I think we are more than 45 plus 10 seconds. Welcome to the second talk in the morning. It's by Professor Futaki from actually YMSC, so a local here. And he will talk about Cartan geometry and infinite dimensional Kempf-Ness theory. Welcome him.
Thank you. Thank you for the introduction. And also, thank the organizers for invitation. So I talk about the Cartan geometry and infinite-dimensional Kempf-Ness theory. It's a joint work with Tobias, Diez, and Tudor, Ratiu. In this talk, we propose infinite-dimensional Kempf-Ness theory in the abstract setting of Cartan geometry. This theory can be applied to, for example, Kähler geometry, Ratiu and Donaldson conjecture, and its variants. There are many variants of this conjecture. And geometry, Hermitian vector bundle, Hermitian Young connection, or Hermitian Einstein matrix, and its variants. The motivation is this. Kempf-Ness theory characterizes the GIT, geometric variant theory, stable orbit of a reductive group KC action by the existence of zeros of the moment map of Hamiltonian K action. Here, K is a compact Lie and KC is complexification. It's a finite dimensional geometry. But for example, Futaki Donaldson, Donaldson picture characterizes the existence of constant scalar curvature Kähler matrix by the existence of zeros of the moment map for the action of Hamiltonian diffeomorphism group K. But there's no complexification for Hamiltonian diffeomorphism group. As a remedy for this, we consider Cartan geometry. So this is the motivation. So what's Cartan geometry? I start with Klein pair. Klein pair is a pair of two Lie algebras, A or A or G. I don't speak German, but I should say A or G. And G is the subalgebra R. We assume that G has a Lie group G, but we don't assume R has a Lie group A. And another assumption is that there exists a representation which I denote by at of G to the algebra A, R, and that respect to the adjoint action of G on G. So, for this reason, I denote by at, but it's not adjoint. It's similar. It's something like adjoint action, R, but it's not real adjoint action. And we refer to this setting by saying that R G is a Klein pair with group G. So this is the Klein pair. Again, this is a pair of the algebras, the subalgebra, and G has a Lie group G. This is Klein pair. As I said, we do not assume the existence of A such that the algebra of A is R. Example in Kähler geometry is this. Let M omega be a compact symplectic manifold or Kähler manifold. And then the Klein pair in this case is this Lie algebra and this Lie algebra. This X and omega is the Hamiltonian vector field. It's the vector field that preserves symplectic or Kähler form. And R is X plus I of Hamiltonian vector field. So I put I here, but just for convenience. You may ignore this I, but it's more convenient. I here. So this gay is a Lie subalgebra of this R, and symplectic diffeomorphism in the Lie algebra of this symplectic vector field. So this has a Lie group G, but this doesn't have a Lie group. So this is the main example in this talk. And another example is Hermitian vector bundles. In this case, E is the homomorphic vector bundle, and fixing a Hermitian metric H, we may take the Klein pair of gay E and UE. So UE is the skew Hermitian gauge group, endomorphisms, and this is the full endomorphisms. In this case, this is the complexification of this is just this. So it, as a Klein pair, this is well, most typical. And in this case, UE has a group G, but still this also has a group. In this case, this is two main examples. And then Cartan geometry modeled on the Klein pair R gay with group G on the manifold B is a principal G bundle pi from P to B. In typical example, B is actually, in the Kähler example, B is the space of Kähler forms. P is something different. So I show what this is later. Then together with the G equivalent one form theta with value in R from P, that induces an isomorphism of tangent space of P to R for every P. So in this case, this is TP is product isomorphic to P times A, G equivalently. And also that theta gay star is equal to, the Xi star is equal to Xi, where Xi is in gay and so this is star means induced vector field for the infinitesimal action of gay. So in other words, it is a fundamental vector field of this gay. So and this is called the Cartan connection. But for principal one, we will consider connection assigning horizontal distribution. But in this case, we don't have horizontal distribution. And this is just sort of product structure of this kind. So this is Cartan connection. And then we work with the left principal bundle G, the left principal G bundle, pi from P to B, instead of right principal bundle. It's a minor thing you need to care about. So usually principal bundle has a right action, but usually, I don't know, it depends on your choice. But we choose left action. In this case, G equivalence is denoted by theta. By this, theta is adjoint times this. For right action, this is adjoint inverse. And then the curvature is capital omega, the theta minus half theta. right action, we have plus here, but for left action, we have minus. They are technical matter, so you don't need to care much about this. And Cartan connection theta is said to be torsion-free if omega curvature takes a value in K, torsion-free. So this is used in the statement of the result, but for actual cases, omega is 0 in Kähler examples. It's a flat. Well, for the statement, we need this. A standard result in the theory of Cartan connections that theta induces a bundle isomorphism of the tangent space of B downstairs with P times G A over G. So this this is space of B is in Kähler example, the space of Kähler forms. So its tangent space is A over G. Tangent space is A over R over G. So it's a Hamiltonian vector fields. Then example, but typical example is in fact is A is complexification, G and B is GC over B. We have left axis, right? This way, and theta being more a Cartan form. In this case, there's a flat, so curvature is 0. So this most typical example is septic, and every geometry with vanishing curvature is locally isomorphic to a homogeneous space in infinite dimensions. But in infinite dimensions, it's no longer true because R may not integrate to a D group A. But in finite dimension case, flat means locally homogeneous. Basic part in Cartan geometry. Now we consider N with a G group action. We say Cartan geometry P theta modeled on the Klein pair R A with group G is said to be an orbit through M if the following holds. Long definition, but typically, Kähler example, N is the space of omega compatible almost complex, the integral, omega compatible integral complex structures. In the Hermitian-Einstein case, it is the space of connections with the curvature type 1 or this with this condition. So the connection A defines a holomorphic structure E. So in the Hermitian-Einstein case, N is the space of A's satisfying this. In the Kähler case, it is a space of almost complex structures. Just, yeah, so the assumption is that there exists a G equivalent map from P to N, which I didn't by chi, such that N is in the image of chi. I think this. So P, actually P is the replacement of complexification of G. So it's like something like a GC, but we have in mind when complexification doesn't exist. So we define something else. It's a principal bundle of a space of Kähler bonds over B. So this should be thought of as a replacement of complexification, and chi is the action of the replacement on the space of almost complex subsets. And M is almost complex structure that you have in mind. The Kähler manifold, almost complex structure of the Kähler manifold you are interested in. So the image of chi is the orbit of P action through M. And then we also consider a least subalgebra R sub M on the right Lie algebra action of Rn on P, denoted by zeta star of P, which commutes with G action, which satisfies this condition. This condition is important. So we consider chi as an action of P on N, and this condition is that this vector field is a stabilizer of this action. So in the case of, in the Kähler example, in the space of almost complex structures, and then stabilizer of complex structure in the holomorphic vector fields. So this is the algebra, so the kernel of action of some group that fixes M, the complex structure is the holomorphic vector fields. And in this case, the vector bundle case, this is this RM is the holomorphic endomorphisms. This is a typical example. And then, so as I said, the tangent bundle is isomorphic to the product. So this, the differential of chi can be regarded as an action of this R or P, or infinitesimal action of this tangent space on the space of almost complex structures. And AM is the stabilizer of complex structure. Also, this is the holomorphic vector fields, for example. And then yeah, so as I said, if A is a Lie group, when R has a Lie group, then this RM is the Lie algebra of the stabilizer of AM. This is the typical example. It's okay. So a Lie algebra action of G on an almost complex manifold. So far we didn't consider complex structure as a space, and we didn't consider complex structure. But here we consider almost complex manifold on N. And then G acts on N, but then complexification of G has a natural linear map to tangent space of N by extending xi1 times ixi2 to xi1 n times j xi2. So I is the complex structure of C, and j is the complex structure of n. Right? And then this image of gay C is given by gay C dot m, and we say Nj is an almost complex manifold, and G is a Lie group acting on N, and then a Cartan geometry P theta modeled on the Klein pair are gay with group G is said to be a model for the complex orbit. So here we consider complex orbit through the point of M. If it is the orbit to M in the previous sense, and we'll assume that the infinitesimal action of chi of P is equal to gay C orbit of chi. So this is assumption for complex orbit. This is assumption. Without only with this situation, this doesn't hold, but we assume this in the definition of complex orbit. Now I come back to Kähler geometry as well as a physics picture. So as I said previously, Klein pair with group G in this case is this, and omega is a compact Kähler manifold. The pair of R and G is this. So G, it's better to start with G. G is the symplectic vector fields, and then R is symplectic vector field time plus I of Hamiltonian vector fields. Hamiltonian, the algebra of Hamiltonian vector fields. And then in this case, this symplectic vector fields has a group G of symplectic diffeomorphism group preserving omega. But this it, this Hamiltonian is a subalgebra of M, and so I'll say. So this has the ham belongs to this, and I ham is this. So this includes complexification of ham. Complexification. Symplectic vector field. Not really. No. It's well known in Kähler geometry that this x and omega is something like this. So up to identified vector field with one forms, this is isomorphic to H1 on M plus half. Hamilton diffeomorphism. This is our chart. So harmonic one forms. If you choose harmonic one form, take the dual vector field with the synthetic Kähler form. And this is harm, and this has this structure. So this has a complex structure, but this doesn't have a complex. So together with this, now together with this has a complex structure. So if I add I ham plus I ham, then this has a complex structure and this has a complex structure. This plus this has a complex structure. This has a complex structure because it's Kähler. So this is the situation here. So this is the Klein pair. And as I said, N is the space of all omega compatible integrable almost complex structure J's of N. So that M omega J is Kähler manifold. Given complex structure, we consider the space of Kähler forms compatible with J. I denote Kähler form by sigma. And then this is P, our P. This is a replacement of complexification of Hamiltonian diffeomorphisms. This was actually introduced by Donaldson's paper. He wrote many papers on simple moment maps. This appeared one of them. So P is a pair of Kähler form and diffeomorphism such that pi star of omega is equal to sigma. So omega is a fixed Kähler form, and sigma is varying Kähler form. For this pair of omega, you have a diffeomorphism pi. So the pair is P theta. Then P is a Fresher principal bundle with a structure group diff m omega of K. Obviously, this has a projection to K by assigning this pair to sigma. So this has a projection from P to K. And what is the fiber? The fiber is phi such that preserving, for example, psi preserving omega. We consider left action, so we have psi, psi, phi, psi, prove is just star, psi star of omega. If this is omega, this is the fiber of the projection. So the fiber is the group diff m omega. This is the fiber of this projection. So this is the principal diff omega bundle of K. So this is our P. So this gives a better understanding of P, but actual computation, well, it's better to understand P as a submanifold of diff M, because if phi is given satisfying this, then sigma is defined. So in this definition, only phi is necessary if this relation is satisfied. So we denote by phi star omega to be sigma phi. So P is only determined by phi with this property. So this P is a submanifold of diff M. So previously, as I said, P, we consider action of P on N. So actually this has an action because this is a diffeomorphism. If you regard this as a diffeomorphism, this happens as action on N. Then here's the Futaki picture. We have an adjoint action on this pair, and we have action on the complex structure by push forward. Then DC is J times DC, so then we have a natural. We have this equation. C phi is a DC operator for phi stars. J, yes, just technical computation. Then the tangent vector of x on P is expressed in this way. So previously, as we defined this way, P is a pair of pi star omega equals to sigma. But this is submanifold in differm, so the tangent vector should be a vector field. This relation determine some relation of some condition of the vector field, vector x. It should be this. So the derivative of x should be ddc of some function from this equation. The tangent vector of p must be something like this, and then x is decomposed in this way. So it's complicated. So omega sharp is isomorphism between one form and vector field. Actually, so inner product of omega is contraction by x and omega, and then use this isomorphism. This actually equals to x. So x is equal to x cells because of this relation. Complicated. Sorry, it's why not complicated. So it looks complicated. It's easy computation. These two cancels, and then we want to define the Cartan connection on P because Cartan connection is the keyword. This is defined as follows. We take symplectic vector field to be this, and Hamiltonian vector field to be this. Here, I replace this j omega by I. And then, obviously, this is a Hamiltonian vector field. This term is a symplectic vector because of this relation. This is a symplectic vector field. So this is this element plus this, and this gives a Cartan connection on P relative to the Klein pair. This. Then, as I said, this chi is a action of P on space of J's by push forward. I identify P as a submanifold of diffeomorphisms. And then the AJ, RJ consists of real J holomorphic vector fields, Z on a compact Kähler manifold, which can be uniquely written as X plus IY. X is a symplectic vector field. Y is a Hamiltonian vector field. And then we can show that this P is a Cartan model of the complex orbit through J. And this Cartan connection theta is flat. This is a bit difficult computation, but we can show it is flat. So it is torsion free. So this is a pretty Donaldson picture that we apply. Then so we develop a Kempf-Ness theory for Cartan geometry with those example in mind. Now, so this is an abstract theory. There are lots of technical definitions. I'm sorry, I have to go through quickly. So a duality of R gay is a map from gay star times R to R. That is adjoint G invariant that vanishes on gay star times gay. So this vanishes on gay star times gay. Gay was a Lie subversion of R. In the Kähler example, complement of gay was Hamiltonian vector field. So we assume this vanishes on gay. That means we only take care of Hamiltonian vector fields. So we don't take care of gay symplectic vector field, and R has a gay plus Ham. So we only take care of Hams. For example, when R is a gay C, we may take K, I don't know, K, R. You imaginary part of the Hamish inner part. Maybe I should Hermitian inner product. R is equal to gay C. So in this case, really a complexification of gay. We just take imaginary part, then restriction gay vanishes. So only we take care of imaginary part. Suppose N is a symplectic manifold with a symplectic G action possessing a moment map J from N to G star. So to develop Kempf-Ness theory, we need moment map. Here we have moment map on N with value in G star. This is the definition of moment map. Pairing of G star element of G gives a function on N. So this is a function on N. The excel derivative is equal to my inner product with the symplectic form. So we assume N is a symplectic manifold. So I didn't define Hamiltonian vector field so far. This is the with this. This is the Hamiltonian function for X. Given a function on F, df is equal to minus Ix, then X is in the Hamiltonian vector field. So moment map is a sort of collection of Hamiltonian functions for vector fields induced by G is G. So this is simply So the theorem is Futaki, Donaldson, Diez, Ratiu. If in the Kähler setting, this is an example of this situation. The Kähler example is this. In the Kähler setting, N will be omega point compatible Kähler structures has a symplectic structure with moment map for the action diff and omega when the restriction to omega, the zeros of the moment map determine the Kähler manifold with constant scalar curvature. So when the group was Hamiltonian diffeomorphism, this is due to Donaldson, Futaki, and Diez Ratiu extended this to diffeomorphism. So in this case, this is not equivariant. So something we have to take care. So we can apply this. Atiabot, Donaldson, this should be period, I don't know. The hormone vector on the case in the space of connection satisfying this equation. Then has a symplectic structure with moment map with zeros determining Einstein-Hermitian matrix or Hermitian-Yamil connections. These are two main examples. So returning to the general setting, sorry again. This is a general, very abstract theory. So we have some complicated assumption. We say that the moment map J of N is R equivariant relative to a pairing of K R or get star times R to R or the Klein pair algebra. If for any P and Z and eta, this relation is satisfied. Remember, theta was the identification of R and tangents of P. So this is just identifying P action, infinitesimal P action at the infinitesimal R action. So this is just infinitesimal, the differential moment map of this vector field defined by element R. This is vector field P. This is differential of moment map. So this is the element of G star. Take the pairing eta, and we exchange G eta and G, and this is a variation G star and this product. Don't worry. This is a bit complicated, but in the typical example, this is satisfied naturally. So you don't need to take worry about this, but just remember that we need this technical assumption, which is expressed as R equivariant, and also non-equivariance one cocycle G to get star of J vanishes. The vanishing of this means J is J equivariant. Vanishing of sigma is G equivariance. What is this? Is this my inverse? Oh, sorry. So if this is 0, this is J equivariant. But as I said, Ratiu, Diez and Ratiu extended to a symplectic group, and it's not equivalent is necessary. And the assumption is that pairing using this car, this car, this is this vanishing star, satisfy this. This also we don't need care much because it is naturally satisfied for Kähler examples or Hermitian Einstein examples. And then choose a Cartan model P theta for the orbit to M using a map kind of P, this is P action on N. Then for Rm, this is a homomorphic vector field in the Kähler example. Then theta P Z depends on the equivariant of P, and one can show J is R equivariant. This is some complicated assumption. But anyway, this we can show that this is actually G invariant. G is the group for the principal G bundle, P, so it descends to a function on the base space. This is a function on the space of Kähler forms. And then the obstruction is that so let N be a symplectic manifold, G be a D group acting symplectically on N with the moment map J, so N is a space of complex structure. G is a Hamid, in this case, symplectic diffeomorphisms, and with moment map. Then let P theta be a Cartan model for the orbit to M, Ka A, the duality of the underlying prime pair. And assume J is R equivariant, and theta is torsion free. Choose homomorphic vector fields AM, and if L zeta star theta takes value in Gay, so you don't, again, this is technical assumption, but actually this is necessary for this abstract setting, but we don't need to worry about this. This is not automatically satisfied for Kähler examples, for one vector quantity examples. Then this F zeta is locally constant. So F zeta is constant on connected components of P, the space of Kähler forms. So in the Kähler geometry, F zeta is associated to this vector field, something called Futaki. Not, we do not, so here, up to here, we do not assume the Cartan model is a complex orbit. So we don't, in this result, we don't need complex orbit. And then, so B is connected, and the zeta takes value in gain, so we don't need to worry about this. Then this F is a map from the algebra of homomorphic field to R is a the algebra character. The algebra we can show. And here we can consider Kempf-Ness functional. The N be a symplectic manifold, let be a D group acting symplectically on N, the moment map J from N to G star. Let P theta be a Cartan model for an orbit through M via the moment map chi, the map chi, the P action on N with criteria again and reality Ka. assume J is R equivalent, the following holds. So this is, I will explain. Then the one alpha on P defined by this, the right-hand side, is basic. Basic means induced from downstairs, B. So this is one form on the space of Kähler forms. So the Kähler setting, we can define naturally, but it can be defined in this abstract setting. And also, external derivative of this alpha is computed in this way. And here this omega, so omega appeared as a symplectic form, but this is here, this same notation is curvature of the Cartan connection. And then, so we assume kappa A vanishes on G. So if theta is torsion free, because then it vanishes because omega has torsion free means omega has value in G, but kappa A vanishes on G. This vanishes. So and then B is simply, if B is simply connected and theta is torsion free, then there is a function Cm from B to R such that alpha hat is deep psi m. So alpha hat is a closed one form, but it is a derivative of some function. This function is Kempf-Ness function, and it is Kähler setting. This is Mabuchi functional, and also in Hermitian-Einstein case, Donaldson functional. And convexity holds in the setting 3. B is a critical point if and only if the moment map vanishes. So this is a restatement of a generalization of constant scalar curvature Kähler metric is a critical point of Mabuchi function. And second derivative is computed in this way. Not so just this way. So far, we didn't assume that symplectic form is non-degenerate. Also, we didn't use complex structure. So from now on, we consider non-degeneracy of symplectic form and consider complex structure on N. So assume now we assume in the setting of complex orbit, so that we consider complex structure on N, and we assume R is G plus IM with G bracket of G IM is equals IM included in IM. We assume that the almost complex J is compatible with the symplectic form in the sense that omega dot J dot is a Riemannian metric. To show non-degeneracy, we need some definiteness and also metric. So that's why we assume this from now on. Up to here, we didn't assume this. And then the second derivative is computed in this way. Imaginary part of Z psi m of the norm square in terms of this metric. So if Z is in the imaginary part in the Kähler setting, Hamiltonian vector field, then second derivative is positive if Z is non-zero, or the action is non-trivial. So this is convexity and uniqueness, the algebra action. So we assume that the algebra action of Rm is integrated to regular Lie group Z on P, and that kernel of the action is P to the AM. This we assume here regular Lie group. It is always difficult to check the regularity of the one parameter group in an infinite dimensional Lie group. But in this case, we have well, we may assume this finite dimensional Lie group, but we have to. This is a general setting. So we assume regular Lie group means we have a smooth one parameter group. So we don't need we don't take care of regularity geodesics in the Kähler setting. So and then P Z01 to P gamma Z. Let gamma Z be an integral curve of theta inverse Z. Z is an element of IM, and then theta inverse vector field on P, sort of Z constant vector field, theta constant vector field, the sixth Z. Then Z0, Z1 are zeros of FC. If Z0, Z1 are zeros of FC, then there is some Z such that gamma Z0, gamma Z1, dot Z. So this we can this is a generalization. But regularity is always difficult. Well, when ignoring that point, this says if there are two critical points, there are two CSCK metric, then there is an automorphism which sends one critical point to another critical point. This is uniqueness up to automorphisms. In Kähler setting, the result theorem of Lohmann-Pilson. But this is we assume the regularity of this curve, and so geodesics are considered. But in this setting, this is the replacement of geodesics. This is easier to treat in this Cartan geometry setting. So maybe I have to finish. I quickly go through, and then what? So with various assumptions, geodesics. So in this setting, we have a natural affine connection on base Kähler forms. With this affine connection, we can consider geodesic, and this geodesic downstairs. If we project this, project this curve, it becomes a geodesic. And also, if M has an adjoint G invariant product, it Riemann metric, the projection of the curve descends to geodesic case. And the stability, we have to say the slope we can define. But again, this is it's always difficult to geodesic rate. And also, it is another problem to reformulate. It's individual problem to reformulate it as a algebraic invariant. Test configurations. And also, we can define extreme vector field. And here's a Kähler case. So we consider symplectic structure on N moment map. So we can change the symplectic structure on N. We have different moment maps and different PDEs. This is such example. Recently, Z critical Kähler metrics were introduced by Darvan, Haram. In vector bundle case, we have Hermitian Young-Mills. That's law of equation, the whole Hermitian equation, Z critical connection, Darvan McAfee and Petnam. So there are many examples we can apply. Thank you very much.
Well, thank you for the nice talk. Are there any questions? Sorry, take the mic because it's for the recording.
I miss a point, but so you are functionally defined locally or globally. I mean, it looks depends on the choice of small some point, and is it defined on
Defined on the orbit. Orbit.
Are there more questions or comments?
Okay, so is it possible to give a new proof of the existence of Kähler-Einstein metric up to automorphism by the final case by using these techniques?
This is a abstract theory. So such an existence theorem is an individual problem. So it's not possible to give such existence. A uniqueness still, we assume the regularity of the curves. So it depends on big assumption. So just we propose how to complexify Hamiltonian Hamiltonian vector case. So that's
Any more? If that's not the case, let's thank the speaker again. And we will continue.